pretty much now what you're seeing, I hope, is you're seeing the kind of thing that I would have on the screen if we were at school.
Yes.
Okay. So, first of all, this was the assignment we had from that first lesson on Thursday. And let's open it up, see if there are any questions you might have on that. Anybody have any questions you want to ask?
I'm good.
Don't be bashful.
Question number 9 was a bugger.
What's that?
Question number 9 was a bugger.
Oh, yeah. Okay, let's talk about number 9. Yeah, I'm glad you asked about that one. Okay. So 9 was that one about the phone calls, and they had those different plans. Okay, and the question was, when will it pay to go from one plan to the other? So, what I'd like to show you is a way that I went at trying to solve this. Okay. Everybody still there? I'm hearing some strange noises. Okay. So anyway, the one plan you pay $1.95. I want to explain this question on the top. Sorry. Excuse me a second. I purposely have this on so I can talk with people if they have problems. Hey, Greek? Yeah, I'm online right now. I'm teaching my class. No, that's okay. I'll call you back later. Yep, bye. Okay, sorry about that. So, the one plan was you pay $1.95. This one right here, you pay $1.95 and then you pay 15 cents for every call over 10. You get your first 10 free. So this X minus 10 represents how many calls are past 10. So for example, if X represented 15 phone calls you made, then when you did 15 minus 10, you would have 5 calls that are over, you know, the 10 limit, and so then you'd have to pay 15 cents times that 5. So anyway, that was the one plan, and then on the right, this plan you paid $9.95 flat rate, and you paid 10 cents, but you got 100 calls free. So do you see what it's saying over here? It's saying, yeah, every call over 100 you pay 10 cents for. The problem is we never get anywhere near 100, so I revised that. There's a case where that equation didn't quite work. You're never going to get over 100 before this deal gets better. So you see how I basically did without that. So now here we are again, $1.95 on the one plan plus 15 cents times every call over 10. Now, you guys see how I got from here to here? I just multiplied 15 cents times X, that's 15 cents times X, and then you have to take 15 cents times negative 10. Anyway, this one turns out to, one way to do it is an algebra problem, and finish the algebra, and it turns out you get, what, 63.3 calls? Well, you can't make 0.3, you can't make 3/10 of a call, so what does that basically mean? On the 64th phone call, you'd be better off. So that answers the question. Now, there's another way to do it too, but I'm guessing, you know, that was, like you said, a stinker. So I'll tell you what, I'm just going to show you the second way this could have been done. We could have put it in a spreadsheet. You guys are seeing my spreadsheet, is that correct?
No.
I'm seeing the problem.
Okay. So the sharing is still not right then. Hang on one more time. Come back here. I'm going to stop sharing for a minute. You should see my picture in a few seconds here. All right, I'm going to go back and reshare. Yeah, for whatever reason, it's not, I'm having trouble showing the whole screen. Oh, here we go. I think I figured it out, finally. Um, Whoop, that's not what we want.
Uh-oh.
Uh-oh.
Hang on. Now you should be seeing my spreadsheet.
Yes.
Yes.
Okay, sorry about that. So here I have the number of phone calls coming down the first column, the price for the occasional plan in column B, the price for the light plan in column C, and then the standard plan is in column D. So why is that? Why is it for one phone call? Why does it cost $9.95 in the standard? Because you agreed to pay $9.95 per month, and then you get those 100 free calls. So this isn't going to be. If you look at that column as I scroll down. Hi, Emma. I'm just waving at my granddaughter through the window. They're out in the front here. Emma, your name just got broadcast over the internet. Okay. They're waving at me through the porch window here. Okay. So if scrolling down now, you can see that $9.95 just basically sticks there all the way until you get down to 100 phone calls right here. So that, anyway, okay, so it doesn't matter. We were to compare what? The occasional plan, was it with the light? Yeah. And the question is, when will the B be cheaper than the C? And if you come down here to 64 calls, I'm sorry, when will the, I forgot the names of it. What is that D called? When will the standard plan be cheaper than the light? And sure enough, right here, 64 calls, look, the $9.95 is finally cheaper because the occasional plan is $10.05. So we did it right. I'll just go back and we'll look at the algebra one more time. You guys are seeing that screen again, correct? Where the problem is with all my blue marks and everything?
Yes.
Yes.
Okay, so you see how that 64 actually did turn out correct. That one was a little bit over the top, but sometimes we need a little bit of a challenge too. But if you had trouble with that, that makes sense. That was a stinker. Is there another one you would like to look at? Anybody else? You can always send me questions later too if you'd rather not do it now. That's fine. But I'll just give it one more shot. Did anybody have? Is there another problem? Like how did you do with? I take it the rest of the patterns weren't that big of a wrestling match, and they weren't as hard.
No, they were good.
So how did you guys do on the shoe problem? Did you figure that one out? Wasn't there one with shoe sizes?
Yep.
Yeah, let's just talk about that briefly and then we'll go on. On 39, they gave you this, the length of the shoe on the top row and I think it's the shoe size on the bottom. Is that how that goes? Yeah. So size 3 is for an 8-inch foot, etc. And then they asked you for size 8, and the problem is it went up by 3s. You know, the shoe size went from 3 to 6 to 9 to 12 to 15 to 18. So what happened is you kind of lost your what? You lost your um, there's 8. So what do you do? So I drew an arrow. 8 would be partway between 6 and 9, right? And in fact, wouldn't it be 2/3 of the way between 6 and 9? That is 2 from 6 out of the 3 for the whole distance from 6 to 9. Well, if that's 2/3, then wouldn't the length be 9 2/3 inches? So you must have figured that out, or you must. Anyway, that one was a bit tricky. One more time. Any questions, or I'll start on the new? Okay, let's dig in new. I'm going to do one more thing here. I'm going to take a different view on my computer because there is one thing I'd like to improve on. No, that's no better. Okay, we'll get out of that. All right, we'll just come back here and we'll use this. All right, so first of all, a little bit of a rehash from last time. You recall that we talked about this idea that math is what? Kind of a language of patterns or finding patterns?
Mm-hmm.
Yeah, we were looking into patterns of different kinds. Well, this is just an article showing, this is how crime solving works all the time. In fact, as you can see on this article, they have caught terrorists on several occasions by analyzing patterns of how things have been done and the timing and all of that type of thing. So I just wanted to share that. And then I have one other little tidbit I want to share. This, you don't have to remember this, but I just want to, it's kind of an interesting little story. The famous mathematician, Carl Gauss. The story is when he was in grade school, he was 7 years old. You can imagine ancient school in the, we're talking late 1700s, and the school teacher not feeling too well, and he says to his students, you know, he's maybe got a headache, and he says to his students, all right, that's it. I want all of you to take out a sheet of paper, write down the numbers from 1 to 100 on your paper, and I want you to add them up. Trying to gain a little bit of peace and quiet. Okay? So, in just a few minutes, Carl Gauss is, ooh, 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 ooh. And you can just hear the teacher saying, no, Carl, I asked you to put down all, you haven't even written them all down yet. Well, what Carl had done is he discovered a pattern. And I just wanted to share it with you. So I'm going to drag this away, and you should be able to see this pattern underneath here. So here's what Carl was thinking in his head. Well, if I put down all the numbers from 1 to 100, starting with 1 in the first column, 1, 2, 3, all the way up to 100, and then next to it, if I wrote the same list backwards, 100, 99, 98, okay, what happens when you total each line? The top line there, 1 plus 100 is 101. The second line, 2 plus 99, 3 plus 98, and he said, holy cow, every line totals 101. And how many lines are there? Oh, there's 100. So all I got to do is take this 101, multiply it by 100, which means all I got to do is throw a couple zeros on the end, except for one problem. I've added up the list twice. So all I got to do is divide that by 2. And you get he got the answer. So just the only reason I'm telling you this story is, once again, pattern recognition can really lead you to an efficient solution. So, okay, so that's, you don't have to worry about notes on that. It just doesn't matter. I just thought it tied in nicely with our lesson last time. Okay, so here we go now. As I told you last time we did what? Lesson 1.1? And I told you we were going to count that as being part of Chapter 2. Well, now we're going to really be in Chapter 2 starting tonight. Lesson 2.1, Sets, title, a problem-solving tool. So this you would want to put in your notebooks. This is the start of your second lesson. And once again, the pictures I put up there are just to kind of give you a concept. As you know, we use the term set a lot, right? We have on this page we have a set of golf clubs, a set of dishes, a chess set, a set of playing cards, a set of tickets, and a tool set. I mean, we use that term quite a bit, don't we? Okay. Just to check, since it's the first night and everything, everybody's still hearing me and everything, and can you see?
Yes.
Yes.
Okay, good. So, only reason I'm showing you this page is just to show you that in this particular chapter, there are 5 lessons. We're doing, we're doing this first one tonight. I just thought I'd show you. Remember, I think I said there were like what? Sometimes up to 7 lessons in a chapter. Well, if you take these 5 plus the one we had last time, our first chapter, Chapter 2, is going to have 6. So, anyway, it's the only reason I'm showing you this, just so you can see how many lessons there are. And here are, again, you don't have to write these down, but these are kind of the objectives we're going to try to cover in our class tonight. We're going to try to figure out, is the set well defined or not? And you're gonna see that's pretty easy. We're going to, in part B, describe a set in words by listing its elements and by using set builder notation. So part B, there's 3 ways I'll be showing you. Part C, tell if 2 sets are equal. Part D, find how many subsets a set has. And then, part E says use the RSTUV method. Well, remember I replaced that last Thursday. I replaced that with a 3-step method that I gave you. So anyway, that's kind of what we're heading to do. You don't have to have those written down. Okay, so one more time, what's a set? Like I told you, I'm into formal definitions. It's just what? A group of objects. A group of objects. A set of pencils. A set of crayons. A set of books. A set, it used to be you'd get a set of encyclopedias. Well, that doesn't happen anymore, but what's that?
Oh, just laughing.
Yeah. Remember when, you probably don't, but they used to have encyclopedia salesmen? Wow. I'm showing my age. My apologies. Okay. In sets, we never list multiples. So, a good example of this is when I was growing up, I was a collector of baseball cards, and I grew up in Milwaukee, and I was a big Milwaukee Braves fan. So my ultimate goal when I was a little guy was to get a baseball card for all of the Milwaukee Braves. That was kind of the ultimate goal. And boy, you remember you'd get these cards, and there'd be about 5 cards, and then there'd be this humongous slab of sugar-encased gum. The more I think about it, holy cow, all that unhealthy stuff we did. But anyway, you'd get your cards, and of course, half the time you'd get cards you already had. You'd get doubles. Well, you don't proudly display your doubles. Your doubles you keep off to the side for trading purposes. Likewise, in a set, you don't put repeats down. So that's a little bit different. We'll practice that in just a minute. Remember I said we were going to, one of the objectives was we're going to be able to write sets three ways. One of the ways is just plain listing them out. And so here is a set listing for the first 10 numbers. 1, 2, 3, continue on, but stop at 10. So I got a little bit of a lazy man's approach to writing the numbers 1 through 10. The only time you are allowed to use that triple dot is when you have a pattern of 3 in front of it. Remember we learned last time that if you only have 2, you don't have enough for a pattern. Remember that? We had that one set that began 1, 2, and we all agreed the next number could be 3, it could be 4, it could be a lot of things. So if you're going to use this triple dot, you must precede it by 3, and like we have here. Okay, so that's a listing. And sorry about my braces, they're pretty ugly. Okay? I don't know, I have a real hard time drawing braces. But we don't want to use just parentheses. That could get confused with parentheses from algebra. Then, the second way to list a set is just describe it with words. Verbal. So, what's another way to describe the first 10 numbers? All counting numbers from 1 through 10. So that maybe I should have put that one first. That's probably the first one that comes to mind. And the third one you're not going to like real much, but it turns out it's pretty important. Without it, we'd be stuck. The third is called set builder notation. Yeah, and I will translate that for you. In fact, I've got it right here in blue. So this thing in black reads all x such that x is a counting number where x is between 1 and 10 inclusive. Now you don't have to know all those words, but here's the kind of the weird part right here, that /x, that stands for all x such that. All x such that. So in other words, here following is my description. It turns out that these top two won't always be enough. So if you're wondering why in the world did we include this third one, I'm going to show you in a few minutes an example. In fact, I'm going to show it to you in the very next slide. An example of where you have no choice but to use number 3. So let's go to that right now. Here are some sets of numbers from mathematics. We got the set of natural numbers, 1, 2, 3, going on forever. Okay. I just use, they call it the roster. It's just the set listing. You just list them out. Why didn't I have an ending number? Because they go on forever. Likewise, the set of whole numbers, same thing, starting at 0. And the integers, negatives and positives, no problem. But as soon as you get to the fractions, the rational numbers, we got a big problem. We can't write like 1/2, 1/3, 1/4, 1/5. I mean, you can do that, but you're not going to get all the fractions that way. What about all the ones that have a 2 on the top? And all the ones that have a 3 on the top? And all the ones that have a 78 on the top? You'll never be done. That's why it says it's impossible on that to give a listing. The only way to do it is to use what I've circled here in black. Guess what? Set builder notation. And this reads all x such that x is a divided by b, where a and b are integers and b can't be 0. The reason for the b can't be 0 is because you guys probably remember this from early math. You can't divide by 0. You get total trash. You try doing it on your calculator and it says error. You just can't do it. The reason you can't do it is, I mean, if whatever answer you come up with, when you multiply by 0, you can't come up with a non-zero number. So, for example, 6 divided by 0. What's the answer? It's not 0, because if it was, it would check. 0 times 0 would have to equal 6, and it certainly that'll never happen. So the point, anyway, this is a set that can only be written with set builder notation. There aren't a lot of those, but there's enough of them that you have to know that. By the way, the irrational numbers, those are like square roots that don't come out even. See, for example, square root of 4 is 2, right? No problem. That's just another name for 2, square root of 4. But the square root of 3, you can never get the answer to. I mean, on a calculator, if you try doing it, you would need a display that's infinitely long. You'll never get there. You know, it's 1.414, and it just goes on and on and on. No pattern, never repeats, never ends. Well, guess what? They too need to be written with set builder notation. So all I'm illustrating to you right now is that maybe isn't the best example, but you do need you need all three of these techniques. Just to repeat what they are again, I'm going to go back to the previous slide. 3 ways to describe a set. You can just list them all out. That's the easiest. Just write them all out, if you can. Or you can describe them with words. That's okay too. And when those fail, you may have to use number 3, called set builder notation. Okay. Moving on. Now, here's a special set. I'm going to think maybe I've been drinking too much at my son's graduation party when I give you this one. It's a set with absolutely nothing in it. Notice this bracket here with nothing in it here. That's one way we indicate an empty set right here. We also use this character, the Greek letter phi. It's literally a set with nothing in it. The null set. I don't know how many of you have a German background, but the German word for empty is null. You know, so if somebody called you a Nullkopf, it means you're an empty head. A null set, yeah, which would not be a nice thing, right? The null set is a set with nothing in it. And we need to know, believe it or not, that becomes important. Next one's really easy. When are sets equal? When they have the same contents. What do you think? Are these two sets equal? A and B?
Yes.
Yeah. It's not important what order contents are in. All that's important is they have all the same elements. So since they all both sets have a 1, a 2, and a 3, we're good. This is legitimate. A is equal to B. Okay, so order is not important. All right, on to subsets. You know sub mean, I don't know if you've ever been into outlining, but in outlining, you know, you have subheadings. Subsets are, you know, just like that. There's something underneath. They're smaller, kind of a portion of. So here's a good example. We have a set, that same set, the numbers 1 through 10. Okay, here's another set, set B. It has the elements 2 and 7. What do you think? Is B a subset of A? And the answer is that yes, it is, because what's in B is also part of set A, right? There's a 2 and a 7 up there, so it is like B is just a portion of A, a part of it. We call that a subset. Make sense? By the way,
Yes.
here's the symbol for that. This big old ugly looking C, actually like a horseshoe laying on its side, that means is a subset of. So this thing right here in the box, that reads B is a subset of A. And in this case, that's true. By the way, what about D? D has the element 0 and 1. Is that a subset of A?
No.
Well, if you peek down here, you can see it's not. Why not? Because there's no 0 in set A. See how I snuck in a new element there, 0? So this reads D is not a subset of A. Going too fast? How are we doing?
Good.
The only thing bad about electronic is, you know, I can't see faces and see if you guys are rolling your eyes or calling for medical attention or whatever. Okay.
You got my
Now-
mom laughing over there.
Well, that's kind of you to laugh. So look at this last one down here. Do you remember that symbol? That symbol stands for the empty set over there. The empty set, it reads, is a subset of A. Well, set A has the numbers 1 through 10. How is the empty set a subset of that? Well, it's because of this. And this is definitely something I want you to put in your notebooks, okay? This statement. Please write this down. The empty set is a subset of every set, even itself. Yes, it's just kind of an agreement we come to, but it makes the whole system be beautifully consistent. So the empty set is a subset of everything. So it makes sense if we just peek back to the bottom of this slide again. When I say on here, the empty set is a subset of A. Yeah, it's a subset of everything. I know that doesn't maybe seem quite right to you, but important that we realize that. Okay, now we have a little tiny problem with the book. Maybe it's not so tiny. If you look right here where the arrow is, I should put that in there. I'm going to take that out because it makes it confusing. But do you see that subset symbol with a bar underneath it?
Yeah.
That means an improper subset. Now, an improper subset, what makes it improper is it's no longer sub. Is a set a subset of itself? No, because it's not a part anymore. It's the whole thing. And so we call it an improper. So all these other subsets we've been talking about back here on this page, all these subsets, B is a subset of A, that's a proper subset. When a set can't be a subset of itself, it can be what we call it an improper subset. In other words, it's got all the elements in it, but it's not smaller. So we call it, it's not really sub, so we use the term improper subset. Now, I got to tell you, the book has that wrong. My apologies, but the book, believe me, is wrong on that. They've got that mixed up. They've got they've got this symbol as a proper subset and the one without the bar as the improper, and it's just the opposite. So this, the horseshoe pointing to the right, that's the proper subset. And this one right here, that's the improper one. And the bar underneath kind of looks like the bottom of an equal sign. That should remind you that's why it's improper, because it's no longer sub, it's equal in size. Okay. Oh yeah, and occasionally when we talk about sets, you will see, I'm not real good at penmanship, but you will see like a script, capital U. That is used to stand for the universal set. And that means, wow, everything, every symbol, every single kind of element in the entire poem. I'll show you an example here in just a moment. I guess let's go to that right now. Well, We'll get there. We'll get there shortly. Here's another. So just write down in your notes for now before I buzz by you too fast. That when you see not a printed but like a script capital U, that is used to stand for kind of like Mr. Everything, the universal set. And we'll show an example in a little while. This funny looking E here stands for these words, is an element of. So here, let me show you an example of how we can use this is an element symbol. Here I'm starting with a set that I just made up. Set A has the numbers 1, 2, 3, and 4. So this statement says 1 is an element of set A. And if you look up here, oh yeah, 1 is in there. 2 is an element of set A. Yep. 3 is an element of set A. Yep. 4. Yep. 5 is not an element of set A. So one more time, the universal what? Slash through a symbol means isn't. What do you think about this one down here? The set with 1 and 2 in it, is that a subset of set A? Well, look up here. Here's set A. It is, right? Because 1 and 2 are also in set A.
Yep.
But
Yeah.
it would be wrong to say this. So don't write this in your notes, okay? This is incorrect. See, as soon as you put braces around it like I did here, it's no longer a number. It can't be an element. Now we're talking is a subset or not. So this is like saying they is coming, where you use a plural subject and a singular verb. It's just improper usage. Or she are nice. You know, here I'm using a singular verb and a plural, a singular subject and a plural verb, and you know that we shouldn't be doing that. Likewise, this is as bad as that. So when you've got braces, then you need to use either subset or not. And when you have just a plain bare number like we had here, then we need to use the funny looking E. By the way, you probably noticed this, but the subset and the is an element are the same, except that one has this little horizontal bar in it, so could be a little confusing. But of course, the is an element, I think what makes that easy is it still looks like an E. So hooked up with the word element. Okay, next slide. Yeah, and I think it was Cindy. We were talking about this when we first got hooked up here today. We were talking about n being how many elements a set has, and you're going to see that's going to be in a formula in a few minutes here. So let's do a little investigation. Okay, right over here on the left, I made up a set that I called A1. And in that set, you see I only have one element, correct? Just a 1. So help me, would you agree that these are all the subsets of that set? Well, first you got the set itself, that's the improper subset. And then, remember, the empty set is a subset of every set. So when we started off with one element, do you see that we came up with 2 subsets? We only had one element and we came up with 2 subsets. All right, let's do the second one. In A2, we've got 2 elements, A and B. So here's all the subsets. The set with just A, the set with just B, the set with both A and B, and there's that crazy empty set again. How many subsets?
4.
4. You following? Okay, let's try this third one. And like I said, okay, I did have a little bit to drink. So you're going to think I've gone off the deep end here. But this time I'm giving, for my set A3, I've got 3 elements: circle, triangle, square. Just so I could be a little different. Here I use numbers in the first set, I use letters in the second set. Here we're using symbols. What are all the subsets of this set that has 3, by the way, 3 elements? Well, there's the one with just the circle, there's the one with there's the singles, you know, just the triangle, just the square. Okay, then how about the doubles? Watch out, there's more than you may think. Because what do we all have here? Plug my computer back in. We've got circle, triangle, circle, square, triangle, square. Those are all the so-called doubles. And then there's the triple. We could have the improper subset where everything is there. Circle, triangle, square. And then don't forget about the empty set. And how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. You may not. You see how that's doubling each time, guys?
Yeah.
Yeah, 2 doubled to 4, 4 doubled to 8. Actually, whoops, wrong device. Here's the formula. My apologies. I went off the page. I'll come back. Here's the get rid of that. Okay. Here's the formula. If n is how many elements the set had, then the number of subsets is 2 to the n power. Now, Cindy, I think this is what you might have been referring to.
Mm-hmm.
So, look down here. Let's take the first one. Here, n is 1. What's 2 to the 1 power? That means 2 times itself 1. Oh, that's 2. All right, when n is 2, what's 2 squared? 2 times 2, 4. When n is 3, 2 to 3 power, 2 times 2 times 2 is 8. Oh, okay. This works every time. So if you just count how many elements there are, and that will be your n, and take 2 to that power, you've got how many subsets there are. And that includes all the subsets, including the empty set and the improper. So there is one more I'm going to share with you at the bottom here. If you only want the proper subsets and you don't want to include the improper ones, well, then you just have to subtract 1 from that. Now, let me give you an example. In Milwaukee or in the area, do we still have Baskin-Robbins ice cream? Have you guys ever heard of that?
Heard of it.
Yeah, well, anyway, on their signs they say 32 flavors. Or no, they say 31 flavors. Okay. So really, think all that. So what does that mean? They have 32 different ice creams? No, it means they have different combinations. Like, for example, you could have, let's say, vanilla, strawberry, and chocolate. Okay? And then you could have, like, vanilla and strawberry, let's say a scoop of each. Or you could have vanilla and chocolate, a scoop of each. You know what I mean? You got different combinations. So if you have 3 ice creams, how many different kinds of cones can you make? Well, what's 2 to the 3 power? 2 times 2 times 2, that's 8. Okay, well, what if we add 1 flavor? We now have 4 base flavors. What's 2 to the 4th power? So just multiply 8 times 2, and now you'd be up to 16. And if we had 5 base flavors, 2 to the 5th power is 32. So you could, if you just had 5 flavors and you were trying to market your ice cream shop, you could say, we've got 32 flavors. So why does Baskin-Robbins claim they have 31? It's all because of one thing. Who's going to want the empty set? Nobody's going to walk up and say, oh yeah, give me a cone. Don't put any ice cream in there. So here the empty set, I mean, nobody's going to be that stupid. Well, I suppose I shouldn't say that. There might be somebody who just loves to munch on plain cones, but that was a pretty rare case. And by the way, if we just added one flavor to that, 6, now you'd be up to 64. And this is, you're going to see there's a hamburger problem in the assignment that goes at this. Instead of different flavors of ice cream, they say, all right, you got a burger. What are all the toppings you could put on? You know, and then you got like ketchup, mustard, pickles, onions, and you could pick a bunch of things like that. And then the question is, how many different hamburgers can you say you can make? Well, I can tell you right now, it's 2 to the nth power. And here, somebody actually might want, what, a plain burger? So then the empty set actually would make sense. So I don't know. I hope you're getting this discussion about subsets. So let me just, before I go off of that, one more time. This formula up in the top right here, subsets 2 to the n. What does n stand for?
Your power.
Right below it, the number of elements a set has. So if we had the numbers 1, 2, 3, all the way up to 10, let's say we had numbers 1 through 10, how many subsets are there? Well, I don't want you to calculate it, but tell me how would we do it? Well, how many elements are there for the numbers 1 through 10?
10.
And
Right, 10. So the answer should be 2 to the power of 10. Let's just quick do it. 2 squared is 4. To the third power, 8. To the fourth power, double it, 16. Fifth, 32.
1,000.
6, 64. 7, 128. 8, 256. 9, 512. And 10, 1024. So for the numbers 1 through 10, there are actually 1024 subsets of that set. And then if you only want the proper subsets, all right, just subtract 1 from that. That's what this formula on the bottom here is reminding you. Okay. Let's take this happens to be one of the problems in the assignment I'm going to be giving you, number 67. And they give you these two sets, A and B. Set A has the numbers 0, 2, 4, ... Do you get what they're telling you set A has in it? What's the pattern?
2, 4, 6, 8.
Yeah, so what the pattern is what? Add 2?
Mm-hmm.
Okay. So you're going to get, basically, isn't that just all the even numbers?
Yes.
Yeah. Now look at set B. What is that? 0, 4, 8, ...
Mm-hmm.
So this time we're going up by 4s, right? Okay. Now, look at the answers to the questions on the bottom there. Is A a subset of B? Well, I know I already have the answer up there, but
Yeah.
you see why the answer? Why is it no? Do you see that not all the A guys are in the B? You know, like right away, 2. 2 is in set A. Is it in set B? No. Okay, we don't have to look any further. All right, how about the second question? Is B a subset of A? In other words, are all the guys in B also in set A?
Yes.
Yeah, because those are all even though they're, yeah. So do you see the difference there, guys? Okay. Good. Yeah, I already told you this, but just a reminder, when you see this weird looking horseshoe with a horizontal line, that's a way of saying is an element of, and then when you put a slash through it, of course, that means it's not, is not. And we've just talked about this. One of the problems talks about hamburgers with all kinds of different tops, and they can use this 2 to the n power in order to come to a solution. So that brings us, how we doing on timing?
Great.
I may have gone just, it's pretty close to an hour, yeah. So here is the assignment. First of all, I want to make sure you understand it. The odd-numbered problems, starting at 1 and ending at 71. And then I did throw in just a few evens. You see that? Mostly this is the odds from 1 to 71. There is also 10, 12, and 14, those evens. Now, I might have been going, I don't know, it's the only thing I don't like. I wind up doing a lot of talking, and you guys don't get much chance. So, is there anything you would like to ask me about from this? Anything you want clarification on?
No, I'm good.
I'm good as well.
Okay. So, I'll thank you for participating in this, and we'll stop the recording. I would say within 15 minutes you should see a link by the videos where it puts the date. What is it today? The 29th, I think?
Yes.
Yeah. So you should see 5-29-16, and that will be the link to the video, to what we just completed here. So if you want to go back and forth, you can.
Bless you.
Thank you.
Thanks. Have a good evening. Sorry that this interrupted your special weekend. Thanks for participating.
Thank
Thank
you.
Thank you.
Good night. Good night.
Bye.
Bye.
Hi, Brandon.